Picture the last time you tried to build an AI agent. You probably ended up juggling prompt templates in one file, tool schemas in another, callback code somewhere else, and a workflow graph tying it all together. Each framework invents its own vocabulary for concepts that programming languages already have perfectly good names for. NVIDIA's new paper asks a disarmingly simple question. What if an agent were just a Python object? That's the entire premise of NOOA, which stands for NVIDIA Object-Oriented Agents. An agent is a class. Its methods are the actions the model can take. Its fields are its durable state. Docstrings become prompts. Type annotations become contracts that the runtime enforces. And here's the clever twist. If you write a method whose body is just 3 dots, the ellipsis literal in Python, the framework treats that method as an agentic method and fills it in at runtime by driving a language model in a loop. Methods with normal code bodies stay as ordinary deterministic Python. So within a single class, you get a seamless blend of code that always runs the same way and code that gets improvised by an LLM, both callable through the exact same interface. To understand why this matters, think about how prior frameworks handle these ideas. LangGraph asks you to describe control flow as a graph of nodes passing typed state. Microsoft's agent framework wants you to build workflows as directed graphs of executors. Google's ADK gives you workflow agents plus model-callable primitives. Even Codeact, the influential earlier work that argued the model should act by writing code rather than emitting JSON tool calls, still leaves you outside the language, wiring things together through a framework layer. The author's insight is that Python already has classes, methods, fields, async and await, exceptions and type hints. Adopt them directly rather than reinvent them, and you get an interface that both humans and coding agents already know fluently because it looks exactly like the code language models were trained on. Think of it like PyTorch's original move. Hide a sophisticated runtime behind a Python native surface so that the ergonomics feel like ordinary programming. Now let's go under the hood. When execution enters an agentic method, the runtime hands off to what the authors call a strategy. There are 2 built in. Predict is a single-shot strategy for classification or extraction. It renders the context, asks the model for a value, validates the output against the return type, and retries locally if validation fails. The default strategy, Codeact, is more elaborate. It runs a loop where the model can either call execute Python to run code in a Jupyter-like REPL session, or call return result to terminate the method with a validated value. Inside that REPL, the method arguments, the agent itself as self, and the module's imports are all injected as local variables, so the model writes ordinary Python against real live objects. This is where one of the paper's most important ideas comes in, which they call pass-by reference. When you call an agentic method with, say, a list of 100,000 rows or a multi-megabyte string, the model never sees the full value serialized into the prompt. Instead, it sees a bounded preview, the concrete type, the true length, and a short head and tail sample. The variable itself remains bound in the execution environment at full fidelity, so the model can slice it, iterate over it, or feed it to another function by writing code. Imagine a chef who gets a recipe card that says you have a 100-pound sack of flour in the pantry, rather than having the entire sack dumped on the counter. The model works on the shape of the data, not on a serialized copy of it. This is what lets the framework scale far past the context window, because the amount of data an agent can process is now bounded by the execution environment rather than by the prompt. The context that the model actually sees is assembled from 3 regions on every turn. There's a static prefix that stays constant across turns, holding things like the system prompt and a rendered documentation view of the agent's own API. There's an event history, which is an append-only sequence of typed events like tool calls, Python outputs, and return values. And there's a dynamic suffix, reevaluated every turn, that shows live state, such as a to-do list or selected fields on Self. This three-region layout is designed carefully for key-value cache reuse. The static prefix never changes. The event history only grows by appending, and volatile state lives at the tail where it doesn't invalidate anything upstream. Both the developer and the agent itself can read and manipulate this context through the same Python APIs, which is the paper's fifth design principle: expose the harness explicitly rather than hiding it in callbacks. There's also an optional long-term memory subsystem, and its design philosophy is worth noting. Rather than run a background extraction pipeline that quietly summarizes conversations, memory here is authored deliberately by the agent through 7 model-callable tools: remember, recall, search, update, forget, associate, and deref. Retrieval combines embedding similarity and keyword matching, then ranks candidates using ACTR-style activation that blends relevance, recency, and importance. Consolidation runs asynchronously between tasks, merging duplicates, resolving conflicts, and pruning stale entries. The entire store is one SQLite file you can inspect, and typed references inside memories resolve against live agent state at recall time, which extends pass-by reference into persistence itself. The empirical results are compelling. On a suite of 88 capability tests run 5 times across 10 models, current-generation LLMs pass 97.9% of runs, with frontier models like GPT 5.5 hitting a perfect score. The stress tests, which probe long-horizon batching, error recovery, and REPL exploration, drop to 84.7% overall and expose a widening gap between small and large models. On SWE-bench Verified, a benchmark of real GitHub issues, NOOA with Claude Opus reaches 79.8%, which is 11 points above the OpenHands v3 baseline that uses the original Codact paradigm, and with GPT 5.5 at maximum reasoning effort, it hits 82.2%. Crucially, it does so with fewer tokens and fewer model calls than competing open harnesses, because tool outputs stay as live Python objects rather than being repeatedly serialized through the transcript. On Terminal Bench 2.0, the advantages are even larger, and the authors trace this to validated termination. Open code stops whenever the model responds without a tool call, whereas NOOA forces the model to return a typed task result with evidence and a verification command, preventing premature declarations of success. On CyberGym, a cybersecurity benchmark, NOOA scores 86.8%, beating most closed-source systems. And on ArcAGI3, the interactive reasoning benchmark, a single NOOA agent with a 50-line skill compresses what was previously a 6-agent world model system and advances the score-cost Pareto frontier, reaching 85.1% on GPT 5.6 at under $20 per game. Now for the limitations. The framework executes model-written code in the agent's own process, which is what preserves pass-by reference, but also means that isolation depends on sandboxing the entire agent process from outside, using a container or VM or permission system. Sandboxed code modes that isolate the interpreter separately would break pass-by reference by forcing serialization at the sandbox boundary, so this is a genuine architectural trade-off. The stress tests also reveal that reliable long-horizon batching, disciplined error recovery, and reusable decomposition at the code model interface remain capability frontiers for smaller models. And while the paper positions NOOA as broadly applicable, the deepest evaluations lean on coding and reasoning benchmarks that already play to the strengths of code-as-action agents. Looking forward, the authors sketch 3 directions that feel promising. First, agent optimization should move beyond prompt search to rewriting the whole agent object, including method signatures, helper code, and context policies, using something like reflective optimization. Second, Skills could evolve from text snippets into full software packages with typed APIs, tests, and versioned interfaces that agents inspect and extend. Third, reinforcement learning could target the richer action space that this harness exposes, teaching models to decide what context to reveal, which variables to preserve, and when to promote a pattern into a reusable library. In that view, the harness is not just an execution environment, but the action space in which agents learn problem-solving structure. Now, let's walk through some questions you might have after hearing all of this. First, why is pass-by reference actually a big deal? Isn't putting data in a prompt basically the same as putting it in a variable? The difference is enormous once inputs get large. When you serialize a 100,000-row table into the prompt, you pay for every token repeatedly on every turn, and you're bounded by the context window. When the model sees only a preview but operates on the live object through generated code, it can slice, aggregate, or transform arbitrarily large inputs while the prompt stays a fixed small size. It also means intermediate results from one tool call become variables the model can reference in the next cell, rather than reappearing as bulky text in the transcript. Second, if the ellipsis body is what makes a method agentic, how does the runtime actually know to intercept it? Python evaluates an ellipsis in a function body as a NOOA that returns the ellipsis literal. The strategy decorator wraps the method so that when it's called, instead of executing the body, the runtime kicks off the LLM loop using the method's signature, docstring, and type annotations as the specification. The docstring becomes the prompt, the arguments become inputs, and the return annotation becomes the validation contract. So the ellipsis is really just a syntactic marker that the developer wants this method's behavior filled in by the model. Third, what stops the model from going off the rails once it's writing arbitrary Python? Several things layered together. Dangerous APIs like eval, exec, compile, and blocking event loop calls are rejected with specific error messages. The return type annotation is enforced, so the method can't exit until the model produces a value that validates against the contract. Errors and tracebacks come back in IPython format with source locations, so the model can debug the way a human would fix a notebook cell. And the deeper answer is that in-process code execution is fundamentally no more dangerous than a shell tool, which most other harnesses ship. Real isolation comes from sandboxing the entire agent process from outside, not from trying to police the interpreter. For large-scale recommendation systems, the ideas here map surprisingly well. Consider candidate retrieval and re-ranking pipelines that increasingly involve LLM-based reasoning over user history, item metadata, and business rules. Pass-by reference is directly relevant. You don't want to serialize a user's 1,000-event history or a candidate pool of 10,000 items into a prompt on every call. Exposing them as live-typed objects that the model previews and manipulates through generated code lets you keep prompts small while operating on real production-scale data, which matters enormously for both latency and cost at billions of queries per day. Typed return validation is equally practical for ranking. Forcing the model to emit a well-formed ranked list with justification fields, validated before the response leaves the harness, prevents the malformed outputs that plague production LLM integrations. The object state and long-term memory design also suggests a cleaner architecture for user modeling. Instead of stuffing user preferences into ever-growing conversation transcripts or opaque embedding stores, you could give each user-facing agent an explicit typed state object with fields the model reads and writes deliberately, plus a memory subsystem the agent curates with importance and recency signals. That gives you inspectability, auditability, and the ability to reason about what the system has learned about a user, which is exactly what regulated recommendation domains increasingly demand. And because the whole agent is ordinary Python, standard software engineering practices like unit tests, code review, and versioned deployments apply directly to agent behavior, which is a considerable step up from managing prompt templates and workflow graphs across a large recommendations team.